In this section, we'll cover an overview of the water cycle. Once we're done looking at the water cycle on a global scale, we'll then take a look at how humans have altered that global water cycle. Only a tiny fraction of Earth's water, somewhere on the order of 0.01%, is in soils where it is accessible to plants and available to support the activities of terrestrial organisms. What this means is that most of Earth's water is actually not available to plants. It's in other different reservoirs. And so changes in and out of this very, very small pool we know are really important, but we have to look at those other larger, more massive pools to understand how much ends up in soil. This is figure 14.3, and this is one of the more complicated figures that we have. It's got a lot of different parts. But it essentially summarizes the global water cycle, and it looks at the pools and fluxes of water on a global scale. The units on this are 1,000 cubic kilometers. It's just a huge number. If you think about what a cubic kilometer would be, and then we're talking thousands of cubic kilometers. And here is the largest pool of water in the world, and that's in the oceans. That's not something that's surprising that it's the largest pool, but on a relative basis, we're talking over 1,000,000 cubic kilometers of water there. So the oceans are the largest pool of water, and when we take a look at evaporation rates coming off of the ocean, we have 436 units of water coming off of the ocean. And I'm not going to mention thousands of cubic kilometers each time, but let's just talk about 436 units coming off of the ocean. Precipitation over the ocean, so how much water comes back down into the ocean, is 391, and that difference is the sea to land vapor flux. So somewhere on the order of 10% of the water that evaporates over the ocean moves onto land and eventually falls. Total terrestrial evapotranspiration is 65 units, which is much lower, but we also have to think that there's a lot less land than there is ocean. In general, evaporation from land is about 15% of global evaporation, but land occupies about 30% of the Earth's surface. What this means is that average evapotranspiration rates are about half as great on land as they are over the ocean. So getting back to figure 14.3, we've got a large flux of evaporation over the ocean, and most of that comes back down into the ocean. There's a sea to land vapor flux of 45 units, and a lot of that falls onto the land. And eventually, a good portion of that gets transpired, with transpiration rates on land being about half of what they are over the ocean. So in total, somewhere in the order of 40% of the precipitation comes from oceans. So 40% of the rain that falls on land originated from the oceans. Total terrestrial precipitation is just over 100 units. 45 of those come from sea to land flux, and not evaporating from the ocean, hitting the land and then being recycled. They were evaporated and then falls on land. So roughly 40% came from the ocean, and 60% is recycling on land. Now we can also take a look at how long water spends in the atmosphere, as well as other different pools, to get an idea of the mean residence time of water in these different components. It's somewhere on the order of 10 days is the mean residence time of water in the atmosphere. Water that enters the atmosphere stays there in vapor form or in clouds, and it's about 10 days before it falls to Earth as precipitation. In contrast, the water that's in soil has a mean residence time, on average, of about 60 days. So there's a lot less turnover of water in the soils. And that means that how much water that you have in the soil is going to be dependent on factors that go back further than just how much water is in the atmosphere. At the other end of the spectrum is groundwater mean residence time, and that can be over 200 years. So when plants extract water from soils, that's water that had recently been deposited in those soils on average. But if it extracts water from groundwater systems, that often has been there for 200 years. Humans, when we tap groundwater for irrigation purposes, again, that groundwater has been there for a long time. And that means it's also going to take a long time, often, to replenish. Quite often, the groundwater that's being tapped is really considered to be fossil groundwater in some parts of the world. So it's water that had been present or would have been deposited in the ground during wetter times than they are currently, and actually would never be or won't be replenished on any reasonable timescale under the current conditions. So let's go back to figure 14.3 one more time. Most of the evaporation that occurs on a global scale comes out of the ocean, and a large portion of that, somewhere on the order of 10% actually, goes onto the land, and that is a major flux of water for precipitation. So we're talking somewhere on the order of 100 units of precipitation on an annual basis, and 40% of those is coming from the ocean. So this ocean to land flux is really big. Once it gets in here, once water gets over a terrestrial system, it's going to spend somewhere on the order of 10 days in the atmosphere. When it enters the soils, it's going to be there for 20 to 30 days, something like that. Now, lakes and reservoirs have different mean residence times based on the size, inflow and outflow, and we talked about that in a previous chapter. And if it enters the groundwater, it's often there for a long time. So here's soil moisture as a unit, 17 units, which is about 10% of all the rain that falls. And that's where we get our mean residence time of roughly 30 days. So groundwater, in contrast, has 23,000 units of it on a global basis. That's large. It's larger than the amount of water in lakes and in reservoirs. But it's slow. There's a slow flux into groundwater and a slow flux out. So we can tap it, it's a large pool, but it's going to be slow to replenish, such that once we tap that pool, in a specific case, it doesn't often go up. We can over tap them pretty easily. Other things, if you spend some time taking a look at the global flux, it'll tell you for water how much precipitation there is in snowfall versus rain, and then how much is stored in glaciers, ice caps, and snow. And you can see that that's a large flux. If we take a look at Antarctica and places like Greenland where we have glaciers and ice caps, there's a huge amount of water that's present in those areas. Lastly, you can take a look at how some of that water gets partitioned, and we'll go through this a little bit later. Some of that water comes onto irrigated cropland, some gets used for industry, a small proportion is used for domestic purposes, and then we've got outflows somewhere on the order of 2. You can see that all the outflows from this system match the sea to land vapor flux, and that's because those two have to be in balance. We're not having a net removal of water from the oceans. So the balance altogether for water entering terrestrial ecosystems and leaving are balanced. There is precipitation that falls over the ocean that comes from the land, but this is just on a net basis. This is our net sea to land vapor flux. So spend a little time with this diagram right here to get to know some of the major pools and major fluxes, understanding how much evaporation there is over the ocean compared to land, and really what proportion of precipitation comes from the ocean.